Well, it's 6 p.m. Eastern Standard Time. I'm Charles Schultz, and this is the Randomizer for February 21st, 2022. And tonight's topic is kinology, and basically it is the study of movement. So this is a term a lot of you have not heard. You might have heard of kinetic energy, which is the energy of motion. Well, kinology is the study of motion, and we're going to get into that and look at the fact that the basic laws of movement and what it all means have been worked out for a couple of thousand years. And yet, somehow, we all seem to have those laws built into our experience anyway, without knowing any of the math. So, right off the bat, I hope that you will go to the SchultzLaboratories.com website or the UniverseScienceCenter.com website. Sign up for our classes. Tonight's class is MetaWorld, and it is lesson 4, and it's all about explosive growth and limits. That class starts at 9 p.m. Eastern Standard Time, and it will be every Monday at 9 p.m. Eastern Standard. And of course, the randomizers every weekday at 6 p.m. Eastern Standard Time. So be sure to join us for those. So let's get to the topic at hand. So, how is it that explaining movement, simple motion, would be a difficult subject? Well, it turns out there are a lot of things that don't make sense right off the bat. Now, anybody knows that you can throw a frisbee to a dog, and a dog can figure out how to catch it. Everybody knows you can throw them a snack, and they can figure out how to get that thing right out of the air. But the dogs don't know mathematics. And when you start and think about it, every one of us is kind of a tyrophysicist in the fact that we understand how movement works. We don't have to know anything about parabolas or acceleration formulas or the force of gravity or anything else, but if somebody tosses a ball to you, you automatically know where that ball is going to be. So what that indicates is that without the use of number, there is a system somewhere in your neural system, in your brain, that is capable of figuring out the path of that ball and what path it's going to follow as it rises and falls. That's kind of interesting. We know that animals can do it or they wouldn't be able to walk around or fly. So why do we have to resort to making a discipline of studying movement? Well, it turns out, as I was saying, that there are some non-intuitive results. And some of them have been turned into some pretty interesting things. First of all, when you talk about an object moving, there are a few things you need to know. How massive is the object? How much force does it take to get it moving? And how quickly will it arrive? So anybody can sit in their car and they can look at the speedometer and it'll tell them you're going 30 miles per hour, for instance. Well, what does that really mean? What it really means is that at that instant, if you were to continue to move at that speed for 1 hour, you will have traversed 30 miles. That's pretty simple, which comes out to half a mile for every 30 seconds, for every minute that you're rolling along. But when we try to put numbers to things, our intuition often fails. It's easy to say, well, this is about a pound or this is about half a cup. And you kind of get an experience from your everyday, just going through life, measuring things, cooking things, moving things. But when we get down to numbers, for the first time, we actually can get a true picture of what it really means. And here's where we get to the oddball part. When you look at an object that weighs a couple of pounds, and I'll say a kilogram. A lot of people don't use metric, but it's very, very easy when you're doing technical things because everything is an exact multiple of 10. And so I like the metric system for that reason. It's very utilitarian. And by the way, we've been moving to metric for quite a while. If you want to know how long, it was originally put into place by one of the presidents, Thomas Jefferson. So we've been a couple of hundred years moving to the metric system very, very slowly. Anyway, that being aside, if you were to have a mass of 1 kilogram, and that's 2.2 pounds, that's a little more than a couple of pounds. It's 2 pounds, 3.2 ounces. And you were to hang that thing on a string, and you would like to know how much force it's going to take for that thing to break that string. Is the string strong enough to hold it? You'd have to ask yourself, what is the mass and how hard is gravity pulling it? Now, we know most strings will hold a couple of pounds without any trouble, but if we really wanted to know the breaking point, how much mass we really could hang on that thing, we'd have to know two things: the mass of the object and the strength of gravity. So gravity does one thing very well around the Earth, and that is it accelerates things toward the Earth. And if you were to measure the rate of acceleration in English units, for every second that you accelerate, you would add 32 feet per second to your movement. It's a little more than that, but close enough. In metric, it's 9.8 meters per second. So if I have a 1 kilogram mass hanging on a string and it's being pulled with enough force to accelerate it to 9.8 meters per second, every second it's feeling 1 g, the force of 1 gravity, the normal on the surface of the Earth. Now, question: how much force would that thing strike if we let it fall? The answer is very simple. You multiply the mass of the object by its speed. So, the speed that it is moving times the mass equals the momentum that it has, the amount of force that it's going to carry. And that force is a definite amount of energy. In this case, it would be, if it were moving at 10 meters per second, just a hair over 9.8, we'll round it to 10 just for convenience sake. If that 1 kilogram mass fell and it struck with 10 meters per second, it would strike with 10 joules of force. So a joule is the equivalent of a watt per second, that much power. So what does that mean? It means that the energy, just like pouring a liquid, would run at a rate so that it would fill up 1 joule if it were pouring 1 watt per second for an entire second. This is the one thing about movement that really fools people who first try to study physics. A watt isn't an amount of power. A watt is a rate of power moving from one thing to another. It's a rate of transfer. So that's like saying gallons per minute. And if somebody said, hey, how much water do you have? And you said 5 gallons per minute. That doesn't answer their question. How long did it run? For a minute? For half a minute? For 5 seconds? The rate is not the amount. It's rate times time that gives you the amount. So these are the tricky things about people first learning physics of movement. Now here's another thing. If you have 1 kilogram of mass, that's like 2.2 pounds, and you shove it, and you keep pushing it, and you push it until it is moving at 1 meter per second, and that's a little more than a yard, the amount of force necessary to get it to that speed in 1 second is 1 joule. So you can measure the amount of capacity of the energy in that object. The funny thing is, if I double the speed of the object, it does not double the amount of kinetic energy it has, the energy of movement. This is the point that gets people. It goes up as the square, not directly. So if you double the speed of an object, it hits with 4 times the force. If you triple the speed of an object, it hits with 9 times the force. If it's moving 10 times as fast, it hits with 100 times as much force. So obviously you have to put that much energy in to get that much impact force out of it. Now, as you would imagine, if you have a friend who's an enthusiast who likes guns or rifles, they often speak about muzzle velocity, how quickly the bullet will exit the gun. And that is their magic number. And a slight increase in muzzle velocity can mean a huge amount of kinetic energy. So the faster you can propel that thing, the much harder it will hit. Not just a little, but a lot. So if you had 100% of your velocity, it hit with 100% of the force. If you had 110%, it hits with 121% of the force, because 1.1 squared is 1.21. So the numbers go up as the square. Now, this is the cool part. Knowing that, if you do the math and you plot it, you get what's known as a parabolic curve. If I take an object and I throw it in the air, it travels in a parabolic curve. So the squares law related to the kinetic energy is also related to the path that it will follow. And if it travels fast enough, that curve can take it completely around the planet before it returns to you, and that is orbit. So some of the important things, the really important things we've learned about movement is that A, it is an extremely effective way of storing kinetic energy and releasing it again with impact, and B, studying the path of thrown objects, we were able to figure out how to put something into orbit. Now, it's interesting, but Galileo, back in the 1600s, was capable of figuring out many of the things about motion. And one of the most important things he discovered is this. He actually went to the Tower of Pisa, the one that leans. He went to the top and he carried different sized masses that he would drop to the ground, and he would time them. Actually, he did another couple of experiments we'll get to in a moment. When he dropped the masses, he found, contrary to popular belief, that a heavier mass did not fall much faster than a lighter mass. The only difference was caused by air drag. If you drop a feather and you drop a small weight that weighs as much as the feather, the weight will reach the ground faster because the feather is interacting with the air and it's drifting down. If you were on the moon where there's no air and you dropped a weight and a feather, they would both fall exactly at the same rate because there's no air friction or turbulence slowing down the feather as it falls. And this experiment was actually done on the moon live. So there are some interesting things that show up. But one of the things that Galileo found was that the movements of things falling from the tower violated the original common sense picture. Now, one of the problems was timing. So instead of just dropping things, which can be very difficult to time, he used rolling weights, a ball, and he put them on a track that was tilted slightly. Now, this was a brilliant move. By tilting the track, you get the downward pull, but it's dividing the strength of gravity to something weaker. So if you put a heavy and a light wheel on two tracks and you let them roll, they would roll at exactly the same time, and he could time that much more accurately. So there are some tricks you can use to lower the influence of gravity, and a ramp will do that for you if you're doing this sort of experiment. Likewise, using a ramp can enable you to have the leverage to move a very heavy object if you shove the ramp underneath it, because by moving it up the ramp, a little narrow, thin ramp, you can move the ramp in quite a bit and jack it up just as if you had a lever in place. So the art of movement and the science of movement are fascinating things when you get right down to it. All of the tools that we use, the screw, the ramp, the lever, the wheel, the pulley, all of these tools are based on using simple principles of physics and moving things through leverage or rotation or direct lifting. And the study of motion has yielded some unexpected benefits. There are some people who create artworks through explosions under plates of metal. And some people have found that they can take pieces of metal with a properly prepared surface, put an explosive against it, and slam it together with the force of the explosive quickly enough to weld it into one piece. That's an unusual way of doing things. It's called hydrostatic forming when you do it in a welded container full of water. If you'll go online and look, the way they create spherical steel tanks is to weld a big geodesic ball, fill it with water, and place an explosive in the middle. And the movement, the expansion of that explosive is transmitted evenly to all faces of the ball, and it blows up perfectly round like a balloon in that instant of time. So the study of movement has given us the ability to put things in orbit, to weld things together, to shape metals, and to plot the path of a projectile. One of the most interesting things I saw was a military weapon called a kinetic weapon. What they would do is they would not put an explosive in the warhead. There is no warhead. The projectile itself is moving so fast that whenever it strikes, it literally vaporizes at the point of contact, and fragments whatever it strikes. Kinetic weapons don't need an explosive because if they're moving fast enough, the energy of the projectile itself is enough to make it molten or incandescent or actually a plasma and burn right through a target. Believe it or not, that's the method they use for stopping tanks in the military these days. It's called a kinetic kill weapon. So, you can also do some very simple things with it. If you apply force to a column of air using ultrasound, you can levitate small objects on the pressure of the air underneath it. There are high and low pressure zones being created by sound waves moving through the air. And by the way, we know how quickly sound moves, and we can tell that it takes about 49 microseconds per inch for a sound wave to travel through the air. That's one of the results of studying kinetics and kinology. So I hope this has been interesting, and I've been all over the map with it. But kinology, the study and the discipline of studying motion, has yielded some very fascinating things in our world. And it leads us to the point of creating gigantic cranes using leverage to move things around and knowing just how much force and load they can handle. It also leads us to safer vehicles. This is why we know that how airbags work safely, the study of movement. So it's an interesting thing, and it's something that requires an understanding of mathematics to fully describe. But the funny thing is, after you've done it a few times, it gets to be very simple. So you might want to look up the laws of motion and Isaac Newton and Galileo and see what they've contributed. I think it would be an interesting read for you. So at this point, I'm going to open for questions, and if anybody has any, the floor is open, and I'll watch your posts there or listen to your voice. Meanwhile, I will encourage you to become a member of Schultz Laboratories and the Universe Science Center to help us fund the development of new galleries and new material. And take your Oculus or your Vive, if you have a 3D headset, get out there and walk around our virtual world and see some of the things we have to offer. It's a lot of fun, and you should get some of your friends involved, let them see it. Become a member, support the growth, and share this with everybody. We want this sort of education to be available for everyone in the world if they just want it. So, meanwhile, let's see if there are any questions. I don't see anything on the floor at the moment. And by the way, our randomizer is going to have a new feature very soon, which I will share with you hopefully tomorrow. We're making some upgrades to how we're going to present our material, and with any luck, we'll have something rather surprising for you. So stay tuned to this channel, as they say. So become a member of Schultz Laboratories or Universe Science Center, and join us every 6 p.m. weekdays, Eastern Standard Time, for the randomizer. Well, I don't see any questions, so I'm going to go to my final few words. I have a quote for you. It's, "He who heeds the world wisely will find good, and whoever trusts in the Lord, happy is he." And that's Proverbs 16:20. So with that, I hope that you will make the world a better place and enjoy your life. Spread this to your friends, share it, and come back and hear the next randomizer. Bring some questions. We love questions. Have a wonderful evening, and thank you for being here.